Now we will move on to a different topic, to a topic concerned about future of medicine. Our first speaker is a man who lost his hands because of meningitis infection. He was a player once. That's why, when he was at John Hopkins University, he and his two friends designed Gear. Gear is actually game-enhancing augmented reality. It allows you to play games even though you have no hands, because you can use your feet. Right now, he is an independent researcher that concentrates on upper limb prostheses, and he wants to develop truly useful robotic hand. Ladies and gentlemen, György Lévay. György, how are you doing, and how is your hand doing?
We're both doing very fine, thank you very much.
I asked this question because when we met yesterday, György told me, oh, my hand is not having a good day. And I was like, why? What's the reason? He said, it's cold outside. Why does she care?
Yeah, that's how it goes. All the environmental conditions, all these wires and electricity around me, they don't go well with my hands. So I'll touch on that a little bit.
Okay, it's up to you. György, please.
Thank you very much. Thank you very much for the introduction and for having me. It's a great honor to be here. I've been a fan of the idea of singularity ever since I was a little kid. I still had hands back then. But the idea that there's a possibility to have humans and computers and machines interact without any type of issue with a natural and seamless method seemed always to tickle me and to excite me. And I really never thought that I'd have the possibility to work in a field that actually, builds towards that. And then around 7 years ago, I woke up one day, I was already at university, and I felt a little weird. Now, long story short, I ended up in a hospital where they told me that they really don't know what's going on with me, so they're going to have to put me in a coma. I woke up about a week later, and my hands, my left arm, most of my skin, my feet, my nose, my ears, they were all black. They told me it was necrotic, and they also told me that I had a meningitis infection, and afterwards I suffered from a septic shock. And what happened that some of my blood coagulated in my veins, it got stuck in the capillaries, and there was no oxygen flowing towards the muscles and the soft tissue, and it just died away. So over the course of the next few months, they kind of scraped away at it, only taking away as much as they absolutely had to, which left me how I look right now. Except for the nose, they did a really nice job with that. I had some great plastic surgeons. But it was a rough time, and I was kind of depressed. And while I was already at university, I was taking a bit of a break to relearn how to walk and so on. I felt I was ready to go back, and so I did, but at that time I was studying things like network theory, mobile networks, systems engineering, stuff like that, and I felt like I now have an opportunity to do something a little bit more personal. So I started learning control theory, and I ended up doing my bachelor's degree in control theory so that I could one day work with prosthetic devices, but let's be honest, Central and Eastern Europe isn't the hub for this kind of technology. We don't have a big need for it. It's not like we have a huge amputee population. But there are other hubs for it, like the United States. So I applied for a scholarship, Fulbright scholarship, which I won, and managed to go to Johns Hopkins University, which is a great place to do this. I did a master's degree there in Biomedical Engineering, and that's where I was first really exposed to the problems that come along with prosthetic devices, such as control. Now, I very much focused into control because at that time, I already had my first prosthetic device, and I was not happy with it at all. It was something called a direct control myoelectric prosthesis. The myoelectric part, come on. There we go. Stop. Good. The electrical interference. I will mention that a bit later. So the myoelectric part means that it's taking electrical signals from my muscles. These are electromyograms, and it's using that to give some sort of control signal to the prosthesis. The direct control part of it means that it's taking signals directly from specific muscles. So in my case, those muscles were, for my left arm, the biceps and the triceps, because they were the biggest antagonist muscles that I had survived. So they put 2 electrodes on there, and they said, okay, from now on, when you flex your biceps, the hand is going to close. When you flex your triceps, the hand is going to open. That is not how our hands work, and it is very underwhelming when you have to use it along with a wrist and an elbow. So I was not satisfied and started looking into, okay, what can we do, or what is out there to make this better, and found that the edge of the research right now for surface, so non-invasive technology, something called pattern recognition. So by the time I got out to Johns Hopkins, I already knew about it, but I didn't know much. So I started learning there, researching at the best labs possible. And this lab had a translational business partner, which is called Infinite Biomedical Technologies. That's where I work to this day. And the goal of our company is to make sure that these new technologies that emerge in laboratories get to the users as fast as possible, because the users really need them right now. So we build accessories for prosthetic devices. It's a small company. Accessories like flexible batteries, because if you think about the battery that's in your mobile phone, it's like a brick. Like where are you gonna fit that? It's hard to fit it in there because the real estate in these devices is very valuable. And the further away you put heavy things, the heavier, the harder it is to control it and manage it. So we started building flexible batteries so that they can take the form of the patient and take the form of the prosthesis. And we also started working on different types of control strategies, things like RFID tags. So for instance, one of the controls is that if I'm using my hand and I open it and I try to grab a cup, I don't want to drop it, because sometimes, as you saw, it moves on its own, and sometimes it opens, and sometimes the glass drops and it breaks, and I get water on myself. If I'm lucky, if I'm not, it's hot coffee, which happened more than once. So I wanted to make sure that it doesn't work. I take this RFID tag, I move it over, and it's going to lock it in place. I'm not going to be able to control it. So if that tag is under my watch, it's not like I'm using another hand to do it. It's an easy way to make it a bit more functional and more accessible for people. Something on the other end of the spectrum, more efficient, is this pattern recognition control, which is built into my prosthesis right now. And the idea behind it, I think, is fantastic. I fell in love with it the first time I heard about it. It uses the same myoelectric signals that simple direct control thing used. But instead of looking at, okay, which muscle is doing what specifically, it employs machine learning and a larger array of electrodes, in my case 8, to make sure that we get a bunch of data and that we can use that data to do more complex calculations and achieve a better control. So in this case, I can, with this control setup, I can extend the elbow and I can bend it. I can bend it. I can open the hand. Boy, it's not helping me out today. I can open the hand. There we go. And I can... Come on. Come on. What am I standing close to here? Something that is significantly affecting my ability to control the hand. Because this should be rotating. Ah, there we go. Okay, so it's closing, it's opening, and it's not rotating properly. Yeah, that's how it goes when these signals are being used. These signals are incredibly noise sensitive. They're noisy on their own to begin with, but the problem is that in some cases, noises like electrical signals amplify and make it incredibly hard for the machine learning algorithm to differentiate between the different classes that I taught him. So before I came up here, I made sure to teach it what I wanted to know. So opening, closing, rotating of the wrist. And by the time I got up here, I went through a few heavy electrical systems. There we go. Now it's starting to work a bit more. And the noise just makes it harder to control. Now, the question might be asked, why don't we use better algorithms? And that's a very valid question. But the problem is there are some very significant constraints on how this has to work. Because, first of all, and this is probably the most important, it has to be real time. If I'm not able to control it exactly when I wanted to control it, then it's really not going to do me any good. Anyone here would be, unsatisfied with their hands if they had to wait a few minutes before it did something. The other thing is that it has to be relatively robust. I can't drop things all the time because I'm just not going to continue to use it. And then finally, it has to be relatively low cost in terms of energy and expenditure, because I'm carrying everything with me. If I have to carry that all day and all the extra battery and all the computational power, it's a burden. So what fits all of these? These are relatively simplistic machine learning algorithms. What we use in this case, or in a lot of cases, not sure, what I will show a little later on definitely uses that, is something called linear discriminant analysis. It basically draws lines in space and then says, okay, well, this incoming point is on one side of the line, this other point is on the other side of the line, and so that way I can tell this should have been open or closed. But that makes it pretty inefficient in the sense that it cannot adjust to things like noise. If the prosthesis moves around my arm, it's going to have differences in the signals that it generates, and the patterns are going to be different. It's not going to recognize them, and I'm going to have trouble controlling it. So what we're trying to do right now, where the research is going, is trying to find better algorithms that can run real time, that can run efficiently. And as, of course, computing power gets better, so do these algorithms. And hopefully one day we won't have to worry about too many wires around us. But that's still a ways off. So I think that as a next step, what I'd like to do after seeing how this has been a bit sketchy, I'm going to do another very stupid thing that anyone who's ever done research or has ever presented or done anything of the sorts knows. You should never do a live demo. That's a bad idea. So I'm going to do a live demo, and I'm going to do the other mistake of asking anyone from the crowd to come up and help me. Because what we're going to try to do is control this prosthesis with that armband that's going to be on someone else. And is there anyone who'd like to try that? Oh, okay, come on. You're the first. Oop, there we go. So I'm going to give you this and pull it on one of your arms.
How far?
Maybe on the left so that we're both lefties.
Oh, okay.
All the way up.
Here?
Let me check if it's in the right orientation. It is not. You have to flip it. In terms of, you'd have to take it off and flip the whole thing.
Maybe I should put this down as well.
Sure, go ahead.
Like this?
Upside down? Like that, yes. So let's try and set this up. As a part, I'm sorry I'm turned around, but that's the only way you're going to see what I'm going to see here. And I'll be turning back around in just 1 second. So I'm going to ask you to extend your wrist, which is if you put your hand up like this, you can leave your hand open. And if you push your wrist backwards like that, is it doing something?
If it's vibrating?
Yes. Is it vibrating?
Not much.
That's okay.
Oh, it is now.
Okay. So do that movement, please. Just continuously. Is it still not vibrating? No. That is bad news. Okay, wait. We might have...
No?
Yeah, good. We're lucky. It's actually you know, might be going okay. So let's connect and let's show some signals. Oh, there we are. So let's hope that it's going to be visible on the screen. So can we get a close-up of the screen? Is that the max? Ah, there we go. So those are his myoelectric signals. And what those signals are doing is showing pretty much which muscles are being activated. And while we don't have a direct map to his anatomy, it doesn't matter to us that much. All it's going to matter is that if we teach a machine learning algorithm, it recognizes it. So keep your hand like this, right next to your body, and do a hand close for me. Yeah, like that. Keep it that way, and now rest your hand. You can let well, not that much. Keep it up here and rest this part of your hand. Right, perfect. So what you see is that part in the middle that's active, that's the pattern associated to his hand close movement. Now if you open your hand, open, just keep it open. You can flex your fingers outwards a bit. Yeah, there we go. So that's open. So you can rest now. And you see that there's a difference in the pattern. It's not really significant to the naked eye, but it's there. And so you can rest it again. And now rotate your wrist in one direction. A bit harder. Okay.
You can really see the difference when I'm using it hard.
Yeah, and you can rest now. You can rotate in the other direction. See, again, different muscles, and you can rest now. And finally, can you extend the way you did right at the beginning? Right? And you can rest now, and you can flex, which is downwards, exactly. And you can rest now. So you can see these different areas where you're getting that different pattern of signals. And we're going to teach a machine learning algorithm to recognize that. But there's something very important, though, is that even when he's resting and not doing anything, he's still getting signals, right? So from the machine's perspective, that's as same a movement as any other, even though for us it's, of course, not. So it's very important that your rest, when you're like that, it stay consistent and it doesn't activate anything, because that's what it's going to learn to make sure that when you're not doing anything, it knows that you're actually not doing anything. So you're going to have 6 movements, which is actually 7 different classes. And those are going to be the movements that hopefully you're going to be doing on this hand as well. So this is where the fun part comes in, because I need to connect. Sorry, I'm showing my backside. What I'm doing is turning everything off, because as we know in technology, turning stuff on and off always helps. That's just common sense. 90% of errors, you turn stuff on and on, off and on. So I'm going to ask you to come here, right here, and you're going to see images of the movements that we just did. And anytime you see an image, you do that image. And make sure your hand always stays in this position. And try very hard to make sure that when an image is done, you rest. So, for instance, if you're doing a palm down, which is rotating your hand down, if a close comes after that, you don't go to close immediately. You go back to normal, and then you do a close. Okay?
What's the default? This or this?
Whichever you want to be the default. So that part is up to you. Now let's see. Okay, so I'm going to press the button and it's going to start. Palm up is when you're rotating your wrist.
So always when there's open, I should stretch out?
No, so there's going to be, the things are going to be written here, or it's just going to be written on the screen. So if you have, for instance, a palm up, you don't do anything with your fingers, you just rotate your wrist. If you have a palm down, again, you just rotate your wrist. If you have wrist flexion, extension, adjust the wrist. But when you have a close or open, you do just the fingers and the hand and not the wrist. Okay?
May I ask you for your name, please? Martin. Okay, Martin, I will equip you with the microphone. We can hear you, and actually, could you put it in your pocket, please?
Yes, of course.
We can experience it from the first-person view. And please do not hesitate to add commentary on what you are doing, we can enjoy it with you.
Sure.
Yeah.
So I'm going to start and just focus on this and do what's said. And there's going to be 2 rounds of all the movements. So here we go. Exactly. It's just palm up. Now rest. Do nothing. Now palm down. Now back to rest and wrist extend. That's upwards.
Does this?
Yes. Now hand closed. Now hand open. Now wrist flexion is down. And this is going to go around one more time. Wrist extend. Palm up. Thank you very much for your patience. I'm sorry, but I've tried oftentimes to talk while this is happening, and it's very hard to concentrate on doing it. So I want to make sure that it goes well the first time so that we can enjoy him controlling my hand afterwards. So as a next step, what I'm going to try to do is connect to my prosthesis. And that's where the tricky stuff comes in. Hopefully, we won't have any issue with it right now. And great. Okay. So put your hand back up here where it was, and just a second. Flex your wrist. Okay, that's a good start. Now extend it downwards. A bit more down. Well, almost. Rotate it a bit. There we go. Down is working now. Yeah. Rest it a bit. Rotate it backwards. A bit more. Stop. Now do an open. Let's see how that came out. It's almost there. Oh, there we go. And you can close it now. Love it.
Oh.
That's very nice, and that's the first try. Now, the interesting thing about that is that when I do this, or at least when I attempt to do it, I do the same thing. I'm trying to move my hand that I don't have anymore. This is called a phantom limb sensation, where my brain still has that part of my body mapped to some degree. And when I try to move it, I can succeed more or less, sometimes less, because there's no feedback mechanism going, right? So when I try to move my hand, I'm not getting any information back to the brain that the hand is actually moving, so it gets stuck. It's like trying to compress a really, really hard rock. And so these are exactly the types of stuff that I try to do. And here's where the next phase of the problem comes in, because it looks nice and it looks interesting that you can control it. And yeah, we're going to try to go a bit further with that, because there's no feedback, as I mentioned, which is a big problem. One of the best forms of feedback that we have is something called proprioception. Has anyone heard about that before? Not a lot of hands shot up in the sky. Proprioception is a very deep and visceral sensation that we have, and we have it all the time. And it allows us to feel our body and know where it is in space, where it's positioned in space. So that's what helps you in the middle of the night when you get a text message and you're just trying to find your phone on the side to bring it in front of you. You can do that because you always know, even with a closed eye, even with it in the dark, where your hand is in space. Now, I don't know that with this. The only feedback I have from it is looking at it. That's some sound, but I can't really map that efficiently to anything. So when I try to pick something up, for instance, let's say this bottle of water, which is neatly tucked away behind the laptop, I have the same difficulties as you're going to have trying to pick it up for me. So let's try and do that. Can you extend it, flex it? No, yeah, sorry, extend it, correct, yeah. Now rotate it a bit. Yeah, nice, nice. Okay, let's go. Can you extend it a bit? Yeah, perfect. Now close. Oh, that's great. I'm going to put this under here. Now, that's definitely... The applause is for you. Oh, you're moving your hand. Watch out for that. Thank you. And so, well, I can't take off the bottle, but I think it's better right now because we have everything full of water here. But now you have to gently try and put it towards my mouth. So, yeah. So there we are. That's how long it takes to pick up a bottle of water and drink from it. And for me, just as much. So I'm going to let you open your hand. Thank you very much. You were fantastic.
Thank you.
And I'm going to disconnect you from my hand, if that's okay. Yes. Would you mind taking that off?
Martin, how did you like your robotic hand?
It was amazing experience. It was...
What did you feel? Did you feel anything, or just the vibration, or nothing at all?
I didn't feel anything, but there were many things going through my mind. Like I can imagine that it's very hard not to have limbs and all this stuff, and kind of magical feeling. You know, when you see that people are suddenly able to do something they weren't able before. So
thank you very much for joining us. Big applause for Martin.
Thank you very much.
Thank you.
Thank you.
Yeah.
You also took the perfect amount of time for me to restart the whole system, so that was great. So it's really exciting, and it's really fun, and you can do it from the outside, and you can do it as a user, but it's still difficult to pull this off, even as a user, again and again and again. So here comes the question, what's missing? What is it that we really could benefit from with these technologies? Well, one of the things is this proprioception, the sense that I really don't know where my hand is in space. I really miss that. I really want to feel that embodiment, and we still need to overcome a few significant hurdles before that happens. Hurdles like direct nerve interfacing. There are very promising research. Great groups are working on it. But, okay, well, if we have that direct nerve interfacing, how are we going to send the signals? What signals are we going to send? Do we really understand how these sensory informations are composed into electrical signals and how they're sent back to the brain so that it interprets it not as a state machine, not as something as, oh, this is cold or this is hot, rather as something dynamic that any position in space, I know where my limb is. It's very complex and probably one of the hardest problems to solve. Another problem is the control. This is great, and I can do 3 separate degrees of freedom, opening the hand, rotating the wrist, and extending the elbow, and so on. But think about how your hand works. You have, just from the wrist and down, over 20 degrees of freedom that you can move simultaneously proportionally, both positionally and velocity-based proportional control. And it's great, but it doesn't really compare, or I should say this doesn't really compare to that level of effectiveness. So sending that control signal back to the hand is also going to take probably direct nerve interfacing and a lot of signal processing. And finally, the suspension. So we have endoskeletons, and we really like it because it's fun and we're soft on the outside rather than having, hard outsides like bugs. But this has to be hard on the outside right now. That's the only efficient way to put it on someone without extensive surgery. So I have a socket going up all the way here. And all the electrodes are built into that and so on. But I kind of miss it having it be connected to my bone, because I can't do this movement. I have to move the hand because the connection isn't tight enough to actually be able to get this kind of movement freedom. So there are these things that are still missing, but there is great work in all areas building towards the solutions. And hopefully, this is my hope, in the next 20, 30 years, we're actually going to have these prosthetic devices, instead of being devices that are kind of an alternative to not having hands or to having hands, they're going to be the cure for amputations. And I like to think about another area of research that was big decades ago. That was voice recognition. It started out as a rehabilitational tool for the visually impaired. Right? They wanted to interface with computers and interface with digital technology. So they started working on algorithms. How can we recognize speech? And there's a lot that goes into that. And it wasn't really a widespread thing until suddenly we reached the technological evolution that processing power is fast and it's great. And now everyone here has a voice recognition computer in their pockets because the companies just bought it up as soon as it came to that level of technology that it's worth it. It's worth it for everyone to use it, not just the people who need it. Now, I'm not saying that I ever think it's going to be good to cut off a limb to put an artificial one in its place, but these technologies have benefits on the side as well. We're talking about how do we get control signals from the people to machines efficiently and seamlessly. That's one aspect of it. The other aspect is how do we get sensory information back to the people from the outside world, the same way that we feel things. Is it possible that we'll be able to see more colors than we can right now without changing our eyes, simply by modulating how our brain interprets what signals? These are areas that stand alone in themselves, but they're also areas that when you combine them, create cool gadgetry and fun technology and useful technology for people who really need it right now. Thank you very much. It's actually working pretty well right now. So.
And you like to have the hand back from Martin?
Yeah, although I actually enjoy it when people mess around with it. It's a fun experience to have someone else control your hand for you.
Justina Radelkiewicz is asking, why the hand cannot be controlled by simple voice commands, open and close?
Well, imagine that problem in a crowded space. Right, someone's saying, "Oh, could you open that door for me?" and your hand opens, or something like that. So there were attempts, but it's not a very practical solution for this kind of technology.
Are you a fan of Red Dwarf?
Red Dwarf?
Red Dwarf, the TV comedy series. Lystra, the cat. No?
No.
There is one part of the series when Lystra is having a prosthetic hand and it misbehaves, let's say, sometimes. And Stepan Klos is asking, does your prosthetic arm sometimes punch people, which you don't like?
Well, by accident, sure.
By accident. Oh, I understand. Say no more.
No, but it would be hard to explain that. Right? The part that I'm missing isn't the part that's really responsible for punching people, however much that would be nice to have. So I can punch myself in the leg because if the hand extends too fast, I sometimes hit myself. But the part I need to actually punch someone, I still have that. So I can't really justify hitting people I don't like in the face yet. Yet.
and could you just pick up one finger? You know, like.
Well, there are ways to trick the system. When it actually. No, I can't do that right now.
You would have to make it ready. Is it right?
Well, there we go.
Which one are you aiming for?
Whichever you'd like. I mean, so yeah, there we go. So you can. It's not a. It was purposefully the design of the prosthesis was purposefully this way, so that if it encounters resistance, it's not going to try and force itself. That makes sure that neither the actuators ever get damaged. Well, not ever, but rarely get damaged. But also it grabs onto objects like that water bottle.
Could someone hack your hand?
Well, I mean, it's possible to hack anything, right?
Yeah.
Elections and whatnot. But
you know something that we don't.
I think everyone knows it, but no one really wants to talk about it. No, but sure, anything is possible. It would be very, very hard. The way I can interact with it is because I know exactly what I need to know for it. And the other thing is that by now there's enough time has passed that the wireless interface is turned off automatically. Yeah. Not just for security reasons, also for security reasons, but also to make sure that it doesn't waste any power. So there are security measures built in. Again, anything is possible. No one has hacked my hand so far.
Yet,
yes.
We don't mean it as a challenge to you, just to point it out.
I wouldn't be surprised, like going home, we'll just start like moving around, grabbing people.
Just be careful.
Yeah.
György Lévay, thank you very much.
Thank you very much.
Thank you very much indeed.
Thank you very much.